All right, folks, let's share this screen over here and we'll get started. Okay, so we're gonna should be over here. Okay, so we're gonna talk about proteins and amino acids today. Remember, I'm gonna go through it pretty quickly. The information is there. I'll kind of hit the high points, and that way you're not watching this video for an hour, which will be pretty good. So when we talk about proteins and amino acids, remember that amino acids are the building block of proteins. And we're not going to go into tremendous detail on how that's done. Just know that when amino acids get together, they need to be bound with a vitamin or mineral, which is a molecule that will give it a particular and unique shape. And so when you combine amino acids with these vitamins and minerals and make you these unique shapes, they can do they do everything in our body. And here's just a quick little slide that shows you all the things that it does do, and it's just about everything. So we need amino acids. We need to eat them. We need to recycle them. There's all kinds of ways that we can get a protein or the amino acids. So because they're vital, we absolutely need them. Okay. So when we talk about those proteins in our bodies that we can use, that we can break down and then use those broken down proteins, which are amino acids, the most abundant are made up of our actin and myosin. Now, please recall a few weeks ago now, we talked about actin and myosin and the sliding filament theory. And if you understand that they're moving all the time, right? We're always making muscle contractions. Then you understand that we break them down a lot too. So we can use the broken down proteins, those amino acids, to make other ones. So that's one of the main places that we get it. They're about 80 to 90% of all muscle protein, your actin and myosin. So they contain all of the natural occurring amino acids that we know of. Okay. The most abundant amino acids that are found there are called branched chain amino acids, and there's a number of them, but I want you to remember these three that are on the screen there: leucine, valine, and isoleucine. Okay, those are the ones that, if I'm going to give you any question on the test, it'll be about amino acids and the names. It'll be leucine, valine, and isoleucine. So remember those. Amino acids are moved around our body through active transport. Another protein called a ligand helps do that. And if you see the picture on the screen, the ligand fits into that protein like a key would fit into a lock. And this works with just about every interaction with the protein. The protein will have a unique shape, and that shape matches whatever it may be needed to do. So if it's a hormone and it needs to stimulate your fight or flight, then it'll stimulate, it'll attach to the cell that is required to get your heart racing faster or your veins to dilate. So that's how it works. It's all about the shape of the protein. So it's the shape that makes it unique. Oftentimes, this transporter we require salts with it or other proteins in order to bind those two together so that we can move them around. Okay, so they're either sodium dependent or sodium independent is basically what we call those. So some of the ligands or some of those messenger proteins or transport proteins, excuse me, either need salt or don't. That's not overly complicated. That's what I don't want to overly complicate it. Just understand that that's why another reason why salt is important in our diets. Now, when you go into other physiology classes and other microbiology classes, you'll have to go a deeper dive into that. But just for this class, understand that sodium is dependent for not only cellular action and nerve conduction, but it also helps move proteins around, those amino acids around to make proteins. When we talk about putting amino acids together to make a protein, we call that protein synthesis. When we break proteins down into amino acids, we call that protein degradation. So while we're young and youthful, we protein synthesize pretty well. And as we get older, we tend not to. So the picture there on the screen is Arnold Schwarzenegger as a young man, and as in that picture, I think he was almost 70. He's in his 80s now. So still looking pretty good for an 80-year-old. So there are some things you can do. Smoking a cigar isn't one of them, but there's some things that you can do to maintain the best possible protein function that you can. And one of those things is to work out and obviously to eat well. Many of you probably already know that Arnold Schwarzenegger has gone primarily plant-based for the last few years. So anyway, just a little tidbit of information there. It's helping him out, looking pretty good. So protein degradation, or the breakdown of protein, serves two purposes, right? We can break down proteins and get those free amino acids can be converted into acetylcholinesterase and used in the TCA, or the Krebs cycle. Remember, the Krebs cycle occurs in the mitochondria of the cell, and it produces ATP along with the electron transfer system, yeah? And that ATP then powers muscle contraction. So we can use protein, break it down, and use those amino acids as part of the Krebs cycle. It's not very efficient. It takes quite a process to get it there, and our body doesn't recognize it very often. So don't consider protein necessarily a fuel. It can be used as one, but it's usually a last resort. We can also break those proteins down into amino acids, and they can be used to synthesize other compounds. And here's a list of them here and what they do. So neurotransmitters, hormones, other peptides and proteins that can help break down foods, things like that. So we use protein for a lot of different reasons in our body. It's obvious. So how does protein degradation occur? Well, one of the ways is through transamination. Simply put, we're breaking carbon chains again. And we use something called glutamate in transamination, and other branched chain amino acids like aspartate and glutamine. And it makes something called ammonia, or NH3. Now, if you look at the molecule over here, right? So you have the amino group, and you have two H's and an N. If you break the carbon chain in the middle, then you free up another hydrogen. Our body does not like to have free hydrogen in it. Hydrogen binds to just about anything. So in order to bind that hydrogen, glutamate helps make this amino group, and harvests that other hydrogen and makes NH3, which is ammonia. And ammonia is toxic to our body. So it then binds with another molecule we'll look at in a second, and is taken up into our urine, or our sweat. So we can get rid of ammonia either through sweating it out or urinating out, which is really nice. It's a really nice process. I want you to be aware of this red square with the R in it. It's called the side chain. This is what is going to give that amino acid combination its unique shape. Typically, this is made up of a vitamin or a mineral, or a combination of them. So this is where that vitamin mineral, or combination of vitamin mineral, is going to sit in this long chain. If you can imagine this being stretched out with a bunch of carbons and a bunch of amino groups and a bunch of carboxyl groups, and all twisted up and forms a shape. What causes that shape to occur is this side chain R factor over here. We can also use oxidative deamination. And basically, we're going to remove that ammonia, right? So we use oxidative deamination to do that. And basically that's just done through the glutamate reaction. Again, don't dive too deep into this. I just wanted to show you, that we can break it down, and that we do get rid of the toxic material that comes with it. This is one of the reasons why we want to stay hydrated, right? And that's why I show you this. We've got to get rid of this NH3, and we do that primarily through our urine and our sweat, and we can't do that, urinate or sweat, unless we're staying hydrated. So another reason to stay properly hydrated is to get that NH3 out of our system. It becomes toxic. Another reason why when you get dehydrated, you feel really bad. So once the amino group is separated from the amino acid, the remaining amino acids form something called a keto acid chain. and that can be oxidized and into CO2 in the TCA. So we can also use this keto acid in the TCA or Krebs cycle. So just another component. Once again, doesn't happen very often. It's complicated to get there, and our body does this as a means of last resort. 6 of the 20 amino acids and proteins are oxidized in the muscle or can be used in the muscle. So take the 2 things that I told you that it's complicated and it's inefficient, and then understand that only 6 of the 20 amino acids that we find in proteins can actually be used in the TCA or Krebs cycle. So those are your branch chain. So those are leucine, isoleucine, valine, and then the 3 listed here. So those are the only 6. So understand once again that if you're taking protein, if you're assuming that protein is going to fuel you, and you're taking a supplement, it better have one of those 6 in there, or you're not going to get any ATP from it at all. Okay. We can synthesize amino acids, so they'd be non-essential. We can make them in our body, and basically we can make them and we can recycle them. So that's very helpful in keeping enough protein on hand. Once again, when we talk about amino acids, glutamate is really the prime mover. It does a lot to help us get rid of NH3, and also helps move what material we can in those amino acids into the Krebs cycle. Okay, so we are dependent on glutamate. So what's interesting about that statement is that when you look at supplements that we can take, one of the main performance supplements is glutamate, and this is the reason why. We naturally do it in our body. We make it in our body. And so manufacturers out there think, well, if it's already good enough for us in our body, well, maybe more of it is better. We'll look later on in the semester at that and understand that sometimes more isn't better. Sometimes more is just waste. And so it may help a little bit if you're deficient, but honestly, a lot of those supplements, we're just overdoing it, and it may or may not help. The amino acids that are not synthesized in our body, we obviously have to eat them. Those are the essential amino acids. So when we look at protein utilization rates and how quickly we synthesize proteins, will give us an understanding of how often we need to eat them. And so when we look at enzymes and hormones, those turn over pretty quick. We're using a lot of amino acids to build new proteins or synthesize proteins for those. So those are enzymes. So if you're using digestive enzymes, obviously they're going to be used up pretty quickly. They recover fairly quickly. So we're talking about recovery here. They have a rapid turnover. So in the test, if I ask you which proteins to have a quick turnover, they're your regulatory ones, the enzymes, the hormones. They turn over within hours and days. Structural proteins, on the other hand, like collagen and contractile tissue, like your actin and myosin, your bones, skin, they have a relatively slow turnover rate. I like to give the example of when you get a paper cut on your finger and it hurts and it bleeds a little bit, how long does that deformed skin then last? So it's about a week. So we know that with the paper cut, the skin is damaged, right? And we need proteins then to fix that and become skin, rejoin the skin. And that takes about a week. So that's a structural protein, days, weeks, and months. Now, if you break a bone, a bit more complicated. Bones take what, 8 weeks? And if it's a severe break, sometimes just a little longer, but average somewhere between 6 and 12 weeks. And that's a long time, right? Our bodies naturally just move the old tissues around and replace them with new ones. And so your liver, for example, takes a couple of months, but in the process of time, all those cells are replaced that are needed, and it takes a couple of months. So those, once again, a structural protein. So recall that on the test when you get there. All right, this is one of my favorite things to talk about. I think it's pretty cool. is tissue turnover. So we recycle pretty good. We're going to use some of those free amino acids in the Krebs cycle, but others can be resynthesized to make other proteins for different functions. And a lot of those recycled proteins come from our gut, from our intestinal tract, which makes a lot of sense, because if you think about it, when you eat something, it's rubbing through all of that tubing, you know, and it's breaking down a lot of the proteins, and you have a lot of enzyme function in there. And so you've got a lot of used up protein material that we can then degrade and take those amino acids and make them into something else. When that occurs, we can actually measure that, and we'll go through some ways that we're going to measure it here in a second. But basically what happens is we recycle about 250 grams. If you're, you know, an average of about 150 pounds or so, you're recycling about 250 grams of protein a day. Your typical requirement for that weight and just normal exercise is about 340 grams. So with that recycled protein, we're only short about 90. So that's where you get your numbers from. That's where we understand that it's about 0.8 grams per kilogram to replace our proteins. If you want to make it really simple, it's about a gram per pound, which isn't really accurate, but that's what or a gram per kilogram, sorry. That's what most people go for, but it could be just a little bit high, but that's a safe number. This is ways to measure it. I'm going to let you look through it. If there is a question on the test, there'll be one and a brief one. So we basically can test urine. Many of you have seen this, or if you've ever thought you were pregnant and used a home pregnancy test, the protein in your urine is what makes that test happen, right? So we can test for different proteins, and the urine is really an easy way to do that. We can also just measure obviously what we intake and estimate protein value of the food we eat, and then we can count the protein excess that we've urinated out. This is a little harder to do because you have to be, you know, pretty consistent with it, but you can. We can do very evasive ones where we can actually look what proteins cross the artery venous through the capillary system. We can actually see what crosses from artery to vein. Very evasive. We don't tend to do that. We can use radioisotopes. We can use tracers, which is another form of like an isotope we can inject into people. We can use this thing called fractional synthesis rate, which is another isotope. So there's lots of ways to do it. And here's the good news. It's been done. It's been done a lot. We have a big data reserve or resource for this. So we're fairly accurate with what we need when it comes to protein intake. We understand pretty well what our body requires. So when we look at different types of requirements for different athletes, endurance athletes don't necessarily need to supplement a protein. They get it in their normal diet. The type of exercise they do doesn't have a overly strenuous demand on their muscle. Although it's hard work, I'm not discounting that. We're just looking at the biology of it. They don't break down protein as readily as a strength athlete. So endurance athletes don't necessarily need to protein supplement or supplement their diets with protein. Strength athletes, on the other hand, only require it temporarily. So their diets will eventually make up the difference. So you don't really need to supplement to improve, right, or to sustain your protein synthesis, as long as you're eating a balanced diet. Now, that is on an average strength athlete. If you're like bodybuilding or getting ready for the Arnold Classic and you're lifting weights 2 or more than twice a day, yeah, you probably need to protein supplement. The recommended daily allowance, as you see on the screen, is 0.8 grams per kilogram. If you want to convert that, it would be ounces and pounds. So you can try to convert that if you'd like. It's 2.2 pounds per kilogram, if that gives you an idea of how to do that. A strength athlete is 1.3, so you're just a little more than the RDA. And once again, you tend to eat plenty. The only time that I would personally talk to an athlete about supplementing is if I know that they're not getting a good diet. So if I know they're missing meals, things like that, then maybe a supplement. But I think marketing out there capitalism, if you will, has done a really good job. And so we have this belief in society that protein supplementing, if you're even thinking about going to a gym to work out, that you better get a protein supplement. And it's not necessarily true. In a lot of cases, it's just a waste of money and resources. So we're still looking at that. They're still studying it. And we've got more people working out and lifting weights now than ever. So at this point, 0.8 grams per kilogram for someone who's not working out. If you're working out really heavy, more than twice a day, then you might go 1 to 3 grams, 1 to 3 grams per kilogram. So just depends how hard you're working out. We do have athletes that are at risk though for protein and carbohydrate. And honestly, I'll say this again, if you're low on protein, you probably are low on carbohydrates as well. So amenorrheic female runners, these are female runners who have missed 3 menstrual cycles in a row. Male wrestlers, gymnasts, female dancers, and usually vegetarian. Although vegetarian athletes may not be as what we thought it was. A lot of our plant-based athletes are doing just fine. There's plenty of protein found in there. It's just not the same. It's just not the same makeup of our branched chain amino acids that we find in muscle tissue that we eat in meat, but it's there. And new research is coming out that tells us that they may not be at as risk as we once thought they were. So, however, if you're limiting your diet to lose weight during an athletic season, that's not good medicine. So we need to figure out a way to keep these athletes lean, but not take away the nutrients that they need. So supplementation usually is the answer to that if we can help them. So those are at-risk athletes. This list will come up over and over again through the semester. So training and protein metabolism, once again, muscle training results in hypertrophy, which can have increase in muscle mass. But once again, endurance training doesn't have a huge effect on this. But we do increase mitochondria and muscle fiber density and things like that. So your protein, you're going to need to take it, right? You're going to still need to eat it. It's going to be used for mitochondria building and for cellular strength and cellular building, but it usually doesn't require so much more that you need to supplement with it or increase protein intake. So we get more and more efficient in the better shape that we get, so which is nice. And the reason why you don't have to supplement it or eat more is because over time we become more efficient at breaking it down and recycling it, which is really nice. So some of the effects, once again, you shouldn't delay protein intake. You should be eating it within certainly 24 hours. It says 24 to 48, but boy, don't be in negative balance for that long. If you run a 5K or a triathlon or some competitive event, don't fast the next day. It's just not good medicine. If you're doing fasting for any other reason, just pick a day that's not after a day that you require more protein. Just don't do that to your body. So pick another day. Manufacturers are getting really, really good at giving us good high quality protein, although once again, it just may not be necessary. So we're still looking at studies on that. So here's a list of the supplements that are out there and what people are saying it does. So we'll go over this list again when we look at supplements. So this is just a quick list. There's like 3 per page. You may need to look over this list before you take the quiz so you know where they're at. Tryptophan is kind of a popular one. We talk about tryptophan when we eat turkey, and Thanksgiving's coming up, so you might want to remember that. So just look through these and kind of get an idea of some of the proteins that are out there and that are being used as marketing to increase the purchase of protein supplements. There they are. So here's your list. Once again, if you have any questions for me, shoot me an email or a text, but I hope this helped kind of clear up some things and give you an idea of where to head with some of your assignments, and that more importantly, you can use it for yourself or to help others. So, okay, guys,